Welcome to Networks Professionals. Introduction. General Architecture and Design.
You know, the internet, it kind of feels like magic, doesn't it? But it's not. It's actually a structure built piece by piece, layer by layer. In this explainer, we're going to build one from the ground up so we can really get our heads around the architecture that powers, well, our entire digital world. So how does it actually work? I mean, it's a question we've all probably wondered about. How does an email from your laptop get to a server halfway across the planet in like a split second? To answer that, we've got to start where any huge construction project begins, with the blueprint. Yep, every great construction project has to start with a blueprint. Before we lay a single cable or configure a single device, we need a universal language, a set of rules that's going to govern how everything connects and talks to each other. This is the conceptual model of our network. And when it comes to blueprints, there are really two big ones to know. Think of it as the theory versus the reality. On the left, you've got the OSI model. It's this beautiful, perfect 7-layer academic framework for how any two computers should communicate. It's a fantastic guide for learning. But on the right, that's the TCP/IP stack. It's the practical, scrappy, 4-layer model that the internet was actually built on. It's the one that's doing all the heavy lifting out in the real world. Okay, so we've got our blueprint. Now it's time to make some big decisions about the physical shape and size of our network. I mean, are we building a network for a small office, or are we trying to build a global empire? The structure we pick here is going to define everything that comes next. The very first decision is all about scale. You've got your local area network, or LAN. That's small and contained, like your home Wi-Fi or the network at your office. Then you've got the wide area network, or WAN, which is what you get when you start connecting all those LANs together across cities, countries, even oceans. And the internet? Well, that's just the biggest WAN of them all, a massive global network of networks. All right, let's talk about our first layout option, the star topology. It's so simple and elegant. Every computer or device, we call them nodes, connects directly to one central hub, kind of like spokes on a wheel. Super easy to set up. But do you see the problem? If that central switch in the middle goes down, the whole network goes dark. It's what we call a single point of failure. Not great. So to fix that single point of failure problem, we have the mesh topology. Now this is clever. Instead of everything relying on one central point, the nodes are all interconnected with each other. So if one connection breaks, no big deal. The data just finds another way to get where it's going. This makes it incredibly resilient, super robust, and it's really a foundational idea for how we built a reliable internet. And if you want to see the modern evolution of that mesh idea, look no further than the spine leaf architecture. This is the go-to layout for today's massive data centers. So think of the leaf switches as the branches where all the servers connect. The magic is that every single leaf connects to every single spine switch, which forms this incredibly fast core backbone. This was a game changer because traffic inside data centers isn't just going in and out anymore. There's a ton of traffic moving between servers. This design gives data a huge number of paths to take, which means wicked high speeds and super low latency. Okay, our physical structure is chosen. We have the frame of our building. Now we've got to bring some order to the chaos. It's time to put up some logical walls inside our network to manage all the traffic and, of course, boost our security. The first tool we're going to use for that is something called subnetting. Basically, we take one big open plan network and we break it down into smaller, more contained neighborhoods, or subnets. This is awesome for efficiency. Why? Because traffic that's meant for, say, the engineering subnet just stays inside that subnet. It's not shouting across the entire company network, which keeps things fast and organized. So how do network engineers define the size of these digital neighborhoods? Well, they use a nifty shorthand called CIDR notation. See that number after the /24? That little number tells you exactly how big the fence is around this particular subnet. In this case, it allows for about 254 devices. It's just a really compact, clever way to define the boundaries. But what if you need to create these separate neighborhoods, but you don't want to buy a bunch of new hardware? That's where VLANs, or virtual LANs, are just brilliant. This is a powerful trick that lets you configure a single physical switch to act like it's several different switches. It's literally like taking one big office floor and just putting up virtual walls to create separate departments. The traffic from sales is completely isolated from the traffic in marketing, even though they're all plugged into the very same box.
All right, our network is built, it's organized. Now for arguably the most important parts, setting up the rules of the road. We have to create a system that directs data where it needs to go, both inside our little network and out to the rest of the world.
A classic way to handle this is with a 3-tier hierarchy. So at the bottom, you have the access layer. That's where you and I plug in our laptops and phones. From there, data flows up to the distribution layer. This is the smart middleman that applies all the rules and figures out the best path for the data to take. And finally, it hits the core layer. This is the super fast backbone of the network, designed to do one thing and one thing only: move data as fast as humanly possible. So how does a piece of data actually get out of its local subnet to reach the wider internet? It uses something called the default gateway. The easiest way to think about it is as the single designated front door for your entire digital neighborhood. Any traffic that isn't for a local address gets sent straight to this gateway. And that gateway is the device that knows how to forward it out to the rest of the world.
We did it. We've built a functional network. But today just functional isn't enough. For our final step, we're going to install the advanced systems that make our network intelligent, resilient, and truly, truly secure.
Okay, first, let's make our network smart. In a traditional network, every single switch and router has its own little brain. This is called the control plane. You have to manage each one individually, which can be a real headache. Well, software-defined networking, or SDN, completely changes the game. It brilliantly separates the brain from the brawn. It pulls that control plane, the brain, out of all the devices and centralizes it. This gives you this incredible bird's-eye view to manage the entire network from one single place. It makes the network ridiculously flexible and way more intelligent.
And finally, security and making sure this thing never goes down. We start with the basics. Redundancy. That just means having 2 of everything critical, right? So if one power supply fails, the other one takes over. Simple. We can level that up with high availability, which uses clever technology to make that switchover happen instantly so no one even notices. And for the absolute ultimate Fort Knox level of security, the air-gapped network. This is a network that is physically completely disconnected from the internet. No cables, no Wi-Fi, nothing. It's the digital version of a sealed bank vault. And just like that, our build is complete. We've gone all the way from a simple idea on a blueprint to a smart, secure global network. Which leaves us with a final question to think about as we move forward. What's going to matter more in the future? Is it the physical hardware, the cables and switches that form the foundation? Or is it the intelligent, centralized software that controls it all? Something to chew on. Thanks for joining us.
Thanks for watching.